Okay, we're talking about, again, this is statics. This is statics lecture 1, part 2. Talking about units and dimensions, we've just introduced a conversion factor. Conversion factor allows us to go from one set of units to another. It's an equivalent amount. 1 kilogram meter per second squared is equal to 1 Newton, meaning the conversion factor 1 would be the same as 1 Newton second squared per kilogram per meter. Now, that's simple, Steve. It's no big deal. It's the metric system. It's easy. Yes, the metric system is pretty easy because everything's one-to-one. It was designed after we kind of understood how to do some of these things. However, in the English, what I call the English, or the imperial system, 1 pound, which is the unit of force, is the amount of force required to accelerate 1 pound mass, an object having a mass of 1 pound, at standard Earth gravity of about 32.2 feet per second squared. I've rounded that to 3 significant figures, which is pretty common for me. I think it's like 32.174, something like that. Meaning that your conversion factor would be 1 pound force second squared for every 32.2 pound mass feet. So what does that mean? That means every time I see a collection of pound mass, feet, and seconds, and I want to go to pound force, then, and I've subscripted here with an F. I'll try not to. I teach thermo regularly, and we have to subscript it there because we use pound mass all the time. So if there's an F, it's a force. If there's no subscript, if it's a force. If it's mass, it specifically has mass, or has a subscript of M. As I mentioned earlier, you probably, in a statics text, won't use the pound mass. There's a good chance you're going to use the slug. So 1 pound is also the amount of force required to accelerate 1 slug at a rate of 1 foot per second squared. The slug is the 1-to-1 unit of mass. Meaning the conversion factor would be 1 pound second squared for every slug foot. So if I have a collection of slugs, feet, and seconds, then it's a 1-to-1 conversion to pound. Just like if I've got a collection of kilograms, meters, and seconds, I can apply this conversion factor, get rid of the kilograms, go to newtons, and just figure out what happens with the meters and seconds. Statics is often pretty straightforward in terms of units. You always want to make sure that they work. That's a good habit to be in, but it's not as critical. Unlike, say, a thermodynamics or a fluid mechanics course, or later on a heat transfer course, where literally your biggest challenge is making sure the units work a lot of times. Here, the units probably work, but it's always worthwhile to make sure. All right. Now, we've talked previously, if you watched my previous video about setting up statics problems, I showed you this process, the problem-solving process. Right? Step 1. What are you looking for? Make sure you write that at the top of your problem. What is it that you're trying to find? Step 2, what is known about that problem? That's often collecting your givens and probably drawing a free body diagram. Step 3 is what laws or equations or tools are useful. Here's for sure where you're going to draw a free body diagram, and you're going to apply, in a statics course, you're going to apply Newton's first law. Because it's static, that means the sum of forces is 0, it's not accelerating. So that's what you're going to, what laws or relationships are useful, that's probably the first one you're going to apply. Then you're going to hit a point, do I have as many equations as I have unknowns? If the answer is yes, then just go do the thing. Go solve. Go do it. If the answer is no, you're going to go back and say, okay, well, what are the unknowns? I've got more unknowns than equations. What are the unknowns? Those now become what I'm looking for. What are some tools that I have to find them? What's known about them? What are tools do I have to find them? Can I generate more equations? Do I have as many equations as I have unknowns? When I hit the yes, solve. If not, loop back and repeat. That is exactly how, I cannot stress this to you enough, that is exactly how you should progress any engineering course. Because again, engineering is all about learning how to solve problems, and statics is very much learning how to solve problems. And why am I going back through this? Well, because that's the next step in my notes here, is this diagram, which is funny because I've not used these notes in probably 3 years, and just the other night I drew this by memory and I came up with almost the exact same process. That says it needs to be repeatable, right? So, all right. Now, if you want to see these units in action, let's see these units in action, shall we? Let's say that we've got an example here. Let me say a person weighs 200 pounds on Earth. Determine their mass in pound mass and slugs. Okay. Well, what are we looking for? We're looking for their mass. And so again, we go back to the process. What am I looking for? You're looking for mass. What is known about the mass? Well, or what do we know? Well, we know their weight. So is there any law or relationship that's going to be helpful if I know the weight and I'm looking for the mass? Well, yeah, we said Newton's law of gravity simplifies down to weight is equal to mass times gravity. If we're on Earth, we get this guy. Right? In any other planet, of course, it's going to have a different lowercase g, but on Earth, g, because they've given me the weight, 200 pounds, and I'm on Earth, so gravity in the English system is about 32.2 feet per second squared, because they told me I'm on Earth, so that's given information, or I can make that as an assumption. So what do we do from there? Well, we're going to say, again, the next step in the process, what's a useful law or equation or tool? I know that the weight is equal to mass times little g. Well, I know weight, I know gravity, I'm looking for the mass. That's one equation, one unknown. Step 4 is, do you have as many equations as you have unknowns? Yes, I've got one equation, one unknown. Now just go solve. So I'm going to say mass is equal to weight divided by gravity. My weight is 200 pounds. Gravity is 32.2 feet per second squared. Okay, so I could calculate a number here. That's fine. I could run this through my calculator. And then I'm going to get units of pound per foot per second squared, which is not pound mass or slugs, really. So what do? Well, I'm going to use one of these conversion factors. Which one do I want to use first? Well, which one do you want to solve for first? So we've written pound mass here first. Let's do it first. So I'm looking for a conversion factor that uses pound mass and pounds. Well, it'd be this guy. Right? Now, like I said, I subscripted an F earlier on accident. That's okay. So I'm going to use this conversion here to go to pound mass. Now, conversion factors are all about what do you have, what do you want, what are you trying to get rid of. I have pounds. I'm trying to get rid of the pounds, so I'm going to put pounds in the denominator. So 1 pound second squared over, and I'm going to put this in the numerator because I want to go to pound mass, so it's going to be 32.2 pound mass feet. And then we look and see, okay, what's left after the units are done? I mean, what falls out, so to speak? This is L1. This is page 3 of something. Well, you can see what happens, I think, right? The pounds are going to go away. I've got second squared divided by second squared. Those are going to go away. I've got feet over feet. Those are going away. All I'm left with is pound mass, and the 32.2 even goes away. So my mass on Earth is going to be 200 pound mass. Now, that's the beautiful thing about pound mass is on Earth, if something has a weight of 200 pounds, it has a mass of 200 pounds mass on Earth. Now, if we go to another planet, gravity is going to be different. Or we go to the moon, gravity is going to be different. So it falls apart off of Earth. But on Earth, if you know the weight in pounds, you know the mass in pounds. It's confusing, but also handy. As I mentioned, you're probably going to use slugs if you use English units at all. So let's do it the slug way. Weight is equal to 200 pounds. That's my weight, divided by gravity, 32.2 feet per second squared. And this time I want to go to slugs. So I've got this conversion factor up here that includes slugs. 1 pound second squared per slug foot. Now, I'm going to have to flip that because I've got pounds in the numerator and I want to get rid of pounds. So I'm going to put that in the denominator. 1 pound foot in the denominator and 1 slug second squared in the numerator. This is the denominator of the denominator, which is still actually the denominator. No, that's not right. It is technically right. Slug feet. I just copied this wrong. You can go back here. I will make mistakes sometimes. It's okay if you make mistakes sometimes too. Try to catch it. But it's notice what we've done here is if we actually look at our units and we're like, oh, I made a mistake because my units didn't work. That's okay. 1 pound second squared for every slug feet. And now my units will work out. So I've got seconds squared divided by second squared. Those go away. I've got feet divided by feet. That goes away. I've got pounds divided by pounds. The only thing left is slugs. 200 divided by 32.2. Normally I would say pause the video here, pull out your calculator, which you could still do. Pull out your calculator and go ahead and calculate this. It's a good way to stay awake. I've already got it done here. So if you go ahead and unpause, I guess now, and if you take 6.21. I'm trying to talk and write at the same time. Sometimes it works. If you calculate 200 divided by 32.2, you should get about 6.21. You might get more significant figures than that, and we don't care. 3 significant figures unless we've got a good reason otherwise. But those are our 2 answers. Your mass is 200-pound mass. I don't think in slugs. I have to convert it by hand, which is okay if you need slugs. I normally don't. That we've already mentioned several times. If not, let's make sure we've mentioned it here. Sig figs. If you gave me that, I don't know what it is, but if you said it's 6.2113728.5, I don't know what it is. That is incorrect. Why is that incorrect? Well, because you can't measure these. You might be able to measure this one. Almost no way you're measuring this one. These are garbage. Absolutely. What are significant figures? Significant figures are what can you accurately measure. 3 significant figures are pretty reasonably priced to measure. 4 is pretty expensive. 5 is really expensive. Anything after that is probably silly, unless you've got something really, really, really expensive measuring that, or you're very, very careful. Do not give me too many significant figures. It's just garbage. For engineers, normally 3 is a good rule, unless you've got a good reason to do anything else. Okay, what else then? I got a minute. We can get quite a bit done in a minute. I find with a statics course, it is always good to do a quick trig review. Trigonometry review. Let's do a quick trigonometry review. This is what I've learned over the years teaching statics. Number 1 rule I have to make sure and be very clear. Theta does not have to be measured counterclockwise from the positive x-axis. And that's not a bad place to stop there, but I'm going to re-emphasize that really hard at the beginning of the next video. I know that's what they probably taught you in your math classes and your physics classes. Theta does not have to be measured counterclockwise from the positive x-axis. It can be measured anywhere you can measure your angle from. We'll pick up there on the next part.